Hey everybody, Dr. A here, and in this video we're going to be exploring another example of average shear stress. So let's go ahead and get started. In the given information, we're being asked to determine the average shear stress in each 3/4 inch diameter bolt and determine the axial reactions at points A and point B in the figures. Okay, so let's take a look at the figures we're given. The first figure we have here is a side view of 3 plates that are bolted together. Okay, notice we have a diagram of a bolt passing through all 3 of these plates. And so I'm going to make a note here. This is a side view here. Okay, we're looking at it on the side. So the middle plate is subject to a 6 kip load that's pulling on it, so that's causing a tensile effect. The top plate has 5 kips directly applied to it, and the bottom plate has 2 kips directly applied to it, okay? And so the connection between the top plate and the wall is A, and then the connection between the bottom plate and the wall is B. Now, if we look at a top view, or we sometimes call this a plan view, what do we see? Well, we see that we, in fact, have 2 bolts here instead of just the one. From the side view, we just see 1 bolt, but we need the top view, or the plan view, to show that we actually have 2 bolts here. Now, the dashed line back here represents the back edge of the middle plate, and the reason why it's dashed is because that's a hidden line. It's underneath the top plate, so when we look at a top view or a plan view, that's going to show up as a dashed line. The solid line here represents the edge of the top plate, so that's a solid line. It's not hidden because we do in fact see the edge of the top plate when we look at a plan view. The 5 kips here, this double vector or double arrow shows the 5 kips pushing on plate A, and then we have the 2 kips that is really hidden. It's really on the bottom plate pulling on plate B, and then we still have that 6 kips out here pulling on the middle plate. All right, so how do we tackle this? Well, the first thing we need to ask ourselves is, what are we being asked to solve for? We're being asked to solve for a few things here. We're being asked for average shear stress in each bolt and the axial reactions at A and B. So we got to calculate a few things here, okay? Let's first start with average shear stress, okay? So I'm going to write solution here, and I'm going to say compute tau average, okay? So we're going to start with the average shear stress, and then we'll get to the axial reactions later. So when we're looking at the average shear stress, the first thing we need to ask ourselves is, are these bolts subject to single shear or multiple shear, right? So is it single shear? Is it double shear, triple shear, quadruple shear, whatever, right? Well, the answer is double shear. Why is that? Well, similar to our other example, there are 2 shear planes. There's a shear plane right here between the interface between the top and the middle plate, and there's a second shear plane here at the interface between the middle and the bottom plate. All right, so 2 shear planes. So we're going to say we have double shear due to the 2 shear planes, okay? So what does that mean? That means that this 6 kips, which is applied axially through this middle plate, is going to get divided between those 2 shear planes. Half of it is going to go to the top shear plane, and then the other half is going to go to the bottom shear plane, and then those each half of that load is going to get transmitted into plates A and plate B. Okay, now let me ask you a question. Is the 5 kips and the 2 kips going to cause a shearing effect through the bolt? The answer is no, okay? The 5 kips up top is being applied directly to the top plate, and it's going to travel through that top plate axially until it gets to the reaction at A. So it's not going to cause a slicing effect through that bolt. Similarly, the 2 kips on the bottom plate will travel axially through that bottom plate, and it will not cause a slicing effect. Think about it, there are no shear planes for that 2 kips to pass through or the 5 kips to pass through to get to the reactions, okay? So one thing that we like to remind ourselves of, and it's really from statics, is applied loads on a system. What do they try to do? They try to take the path of least resistance to get to a reaction, okay, to get to a support. So for this 5 kips to get to a support, the path of least resistance, we sometimes call that the load path, is right through this plate, the top plate. Similarly, the load path for the bottom 2 kips is right through the bottom plate, okay? So the 5 and the 2 kips will never actually go through the bolt in a slicing manner, all right? Only the 6 kips will cause a slicing effect through that bolt, all right? So let's go ahead and tackle this. So I'm going to start with a free body diagram. I'm going to call it FBD1, all right? And I'm going to show that middle plate. So here's that middle plate, and here are the nubs of the 2 bolts, all right? And here is that 6 kips. Here is shear force. Here is shear force V, okay? And so by equilibrium, we can say sum of the forces in the x direction equals 0. Hopefully we can clearly see that V is equal to 3 kips, pointing to the left here, all right? Now what we can do is move to free body diagrams of the top and the bottom plates, okay? So let's look at free body diagram number 2, which is going to be of our top plate, all right? So our top plate is going to look something like this, and we have this bolt here. There's the nub of that, and applied to the top plate, we had that 5 kips from the problem statement, okay? Now, what's happening at the interface of this bolt, right at the interface of the plate where the nub of the bolt is? Well, we're going to have 3 kips right here, pointing to the right. Now, where's that 3 kips coming from? Well, this 3 kips is coming from this force V right here, which is 3 kips. Now, you might be thinking, well, wait a second, Dr. A. I thought you said V is 3 kips pointing to the left. Why are we drawing it to the right in this free body diagram? Well, in free body diagram number 1, yes, that V equals 3 kips is pointing to the left. But free body diagram number 2 shows the other side of that bolt. We're looking at a top free body diagram. So this is like a method of sections type of operations. You can think of a little cut section right here at this bolt and another little cut section at this bolt, and so at the same bolt. So because that's the same bolt but the other side of a cut section, you're going to have a force that is the same magnitude, 3 kips, but pointing in the opposite direction as it did in the previous free body diagram, i.e. it's pointing to the right in free body diagram number 2, whereas in free body diagram number 1, it was pointing to the left, okay? Now, what we're really looking for at this point is the axial reaction. I'm going to call this FA. And so here we can say sum of the forces in the x direction equals 0. And, you know, we can write this equilibrium equation out and show a little bit of work. We can say FA plus 3 kips minus 5 kips equals 0. And so FA comes out to be 2 kips pointing to the right. And that should make sense. I mean, in order to balance this 5 kips pointing to the left, you need to combine 2 kips pointing to the right with the other 3 kips that's already pointing to the right. So you get FA is 2 kips in compression, okay? Pointing to the right, which is pointing into the plate, which is compression, all right? Now, we're going to do something similar. We're going to say FBD3, and we're going to draw similar plate. This is the bottom plate, and here we have that bottom part of the bolt. And what forces do we have here? Well, we have the 2 kips here, and then we have the 3 kips here. Again, the 3 kips is pointing to the right, which is the opposite of what we saw here. V was pointing to the left in free body diagram number 1. And here we're looking for FB, and so clearly we say sum of the forces in the x direction equals 0, and so FB will equal, as you can imagine, 5 kips, and it should end up pointing to the left, which is balancing out these 5 kips, which are pointing to the right. Okay, now are we done? Not really, but these are part of our answers, right? So we got FA and we have FB, but we finally need to calculate that shear stress in the bolt. So we're going to say in the bolts, as 2 bolts actually, we have tau average equals V over A, all right? And what's A? A is the cross-section area of the bolt, so we're going to say pi times 0.75 inches squared over 4. We were told in the problem statement that the bolt was 3/4 of an inch in diameter. So I'm going to say 0.75 squared times 3.14159 divided by 4. So we get 0.442 square inches, okay? And what force do we use for the shear force? Do we use 3 kips? No. We're going to say 3 kips divided by 2 bolts divided by that cross-section area, 0.442 square inches. So really what we're looking at is 1.5 kips divided by 0.442 square inches. And so finally we're going to get tau average is 3.4 KSI, kips per square inch, okay? So one more time, why did we divide this 3 kips by 2 again? Well, we have 2 bolts, right? So going back to the original figure, we have double shear, which means we take the 6 kips and we divide it by 2 shear planes. So you have 3 kips per shear plane, but then you've got 2 bolts passing through each shear plane. So you take that 3 kips and you divide it by 2 again, since you have the 2 bolts. That's how we get 1.5 kips. So be very careful. We're dividing by 2 the first time because we have 2 shear planes. The system is in double shear. We're dividing it by 2 the second time because we have 2 bolts. All right. So that concludes this example. We calculated those axial reactions at plates A and B and the average shear stress in those bolts, in each bolt, and that'll be it. So if you found this video helpful, please hit like and subscribe and be on the lookout for other videos like this. Thanks for watching.